In this lecture, we are going to try to generalize an approach or create a generalized approach to all interpolation problems. First, let's remember that the relations that we created before of polynomial interpolation were all terms of x to different powers. Even the constant term can be presented as something, a coefficient, multiplied by x to the power 0. So we may be able to write now the polynomial as a summation expression, which again can be rewritten in vector form, where h of x is row vector and a is the coefficients vector, a column vector. Each of them can be represented as shown here. You can see here h can extend to whatever extent you want to go through. If you truncate after the second term, then you're using a linear interpolation. If you use the third term, it's a parabola. The fourth term, it's a cubic interpolation, and so on. And the coefficients will go with them in the same way. Then let's use this to use the data that we have, y1, y2, y3, x1, x2, x3, as before, just like we used before. In that case, the x's will appear only in the h row vector, and the a's will stay as is, just constant coefficients. If you repeat this n plus 1 times, which are the number of points you have, where n is the degree of the polynomial, of course, then you obtain n equations, n plus 1 equations. Each has h now, after substitution, is just numbers, and a are unknown coefficients. Let's rearrange this into a matrix form, where you will obtain a matrix with n plus 1 rows and n plus 1 columns. Each row is filled up with the terms that were obtained in each of the h's, h1, h2, until hn plus 1. This, as a whole, can be called the transformation matrix. We'll call it T from now on, where Tij, the general term of T, is xi to the power j minus 1. Again, if you just check for any term, you'll find that I here is the ith point, the ith data point, and j minus 1 is the power that you're going to use in each of the columns of this matrix. Now, this can be solved by inverting the transformation matrix to get A. So if you just get back here, T inverse times y are all points, data points. These are knowns. You know all the points that fill the y vector. If you invert T and multiply it by y, you obtain A. Then let's go back and substitute in the general form here by T inverse times y. So you end up obtaining this relation, which is actually a polynomial. Here, as you multiply T inverse times y, you get a column vector. A row vector times a column vector will end up with a scalar, which is the interpolation polynomial that presents y of x, passing through all the data points that you have. This is the straightforward way of generalizing what we used to do. Now, what if we wanted to present it in a different way? The way that's similar to Lagrange method, for example. Just focus on the other part. Instead of multiplying T inverse times y, let's multiply the h, where h here, remember, h is x's. It's 1x, x squared, x cubed, and so on. If we multiply this h times the T inverse first, what you obtain is another row vector of polynomials. We will call these polynomials n of x. Each of these n's, each of these n of x is just an nth order polynomial with different terms. And if you check with Lagrange interpolation, you can show right away that n j of x is simply the multiplication of the different brackets that you got for that you got through the Lagrange interpolation method. Now you have each of these n's multiplied by a corresponding value of y. That's again just like Lagrange interpolation method. So this is what we usually use in the finite element analysis. Again, the steps are straightforward. Just select any nth order polynomial, create the transformation matrix by substituting different x's, and then invert it. But instead of multiplying it by y, multiply h by it. You'll obtain those what we call in finite element analysis the shape functions. And you can verify all this by yourself. So this is the general form of nj. Nj is a summation of x to the power I multiplied by ti plus 1j, t inverse I plus 1j.